What we're going to do in this video is think about how different functions behave based on how they pair their inputs and outputs. While every function must assign exactly one output to each input, the relationship between the domain and codomain can vary quite a bit. We're going to learn how mathematicians classify these behaviors into three important types: one-to-one, injective, onto, surjective, and one-to-one correspondence, bijective. Understanding these is essential because they form the foundation for inverse functions and higher-level applications in computer science and engineering. Now, here we have two mapping diagrams on our screen. These mappings deal with employees of a company X. One shows employees paired with company's parking space, and the other shows employees paired with their respective working department. Both of the mappings here are functions, but has a difference on their codomain and range character. I encourage you to pause the video and think about the difference between the two mappings. All right, let's look at our first category, one-to-one functions, or what we call injective functions. By definition, a function is one-to-one if and only if different inputs always produce different outputs. In formal math terms, if f of x1 equals f of x2, then x1 must equal x2. Think of this as a rule of no sharing, meaning no two distinct elements in the domain can map to the same element in the codomain.
Let's look at our first mapping as an example, which maps employees to their parking spaces. Suppose each employee is allowed to bring one vehicle to work, and the company assigns only one parking space to each employee. As we can see, the four employees with vehicles are each assigned one unique parking space, as shown in the mapping. Therefore, the function represented here is one-to-one. Notice that there are two parking spaces, P5 and P6, that have not been assigned to any employee. Even though the company has 6 available parking spaces, only 4 of them are currently assigned, because only 4 employees, who are Emma, John, Lisa, and Mark, have vehicles. Therefore, P5 and P6 remain vacant. In this case, the range and codomain are not equal. The codomain consists of all the available parking spaces, P1 through P6, while the range consists only of the assigned parking spaces, P1 through P4. This means that for a function to be one-to-one, an element in the range must not be assigned to more than one element of the domain. In other words, no two distinct elements in the domain can have the same output. Well, what if the function is given as a mathematical expression, such as a linear or quadratic function, as shown here? In this case, we can graph the function and use a visual technique called the horizontal line test. Just like we had seen on the vertical line test, where we check a graph represent a function or not, in the horizontal line test, first we graph the function and we draw a horizontal line across the graph. If the horizontal line crosses the graph at most once, no matter where we draw it, then the function is one-to-one. Here, for the linear function, any horizontal line we draw crosses the graph exactly once. Therefore, the linear function is a one-to-one function. However, if a horizontal line crosses the graph more than once anywhere, then the function is not one-to-one. To illustrate this, let's look at the graph of a quadratic function, which is a parabola. Here, the horizontal line crosses the graph of x squared at 2 points. This means that the same output is produced by two different inputs. For example, when the output, or y value, is 4, the corresponding x values can be either 2 or -2. In other words, both x equals 2 and x equals -2 produce the same output, f of x equals 4. For this reason, the quadratic function f of x equals x squared is not a one-to-one function. Next, let's think about onto functions, also known as surjective functions. A function is onto if every single element in the codomain is the image of at least one element from the domain. This is where the distinction between range and codomain becomes really important. The codomain is the set of all possible targets, while the range is the set of actual hits. A function is only onto when the range equals the codomain. If there are any lonely elements left unmatched in the codomain, the function is not onto. To illustrate this, let's take our second mapping from the introduction, which shows the pairing of employees with their working departments. Here, we can see that every department in the company structure has at least one employee assigned to it. This means that the codomain, which consists of all the departments in the company, and the range, which consists of the departments that actually have employees assigned to them are the same. Therefore, we call this an onto function. However, if there were one department with no employee assigned to it, for example, a department of, let's say, marketing, then the function would not be onto, because that department would be included in the codomain, but not in the range. Also, note that although this function is onto, it is not one-to-one, since departments such as human resources and finance have more than one employee assigned to them. In other words, different employees are mapped to the same department. What about our linear function? From its graph, we can see that the range of the function is all real numbers. Therefore, if the codomain is also all real numbers, the range and codomain are the same, making the function an onto function. On the other hand, when we look at our quadratic function, f of x equals x squared, its range is all non-negative real numbers, while the codomain is all real numbers. Since the range and codomain are different, the function is not onto. But what if our function f of x equals x squared is defined as a function from the real numbers to the non-negative real numbers? In this case, the codomain becomes the same as the range. Therefore, the function is now an onto function. So we need to remember that the domain and codomain specified for a function matter when we classify it as one-to-one or onto. In particular, whether a function is onto depends on its codomain, while the domain also affects the behavior of the function and whether it is one-to-one. Now, this should be fun, because when a function is both one-to-one and onto, we call it a one-to-one correspondence, or a bijective function. In a bijection function, every element of the domain is paired with exactly one unique element of the codomain, which means one-to-one, and every element of the codomain is paired with exactly one element of the domain, meaning it's onto. It is a perfect, unique pairing where nobody is left out and nobody has to share. Let's see our parking space function from before. This function is one-to-one, but not onto, because the two parking spaces in the codomain, P5 and P6, are not assigned to any member of the domain. But what if these two parking spaces are assigned to the remaining employees, David and Frank, as shown here? In this case, all the members of the codomain become members of the range. Therefore, the function becomes onto as well. Once a function is both one-to-one and onto, we can say that it is a one-to-one correspondence, or bijection. Let's look at our linear function as well. As we have seen in the previous sections, this function is both one-to-one and onto. Therefore, we can say that it represents a one-to-one correspondence. What about the quadratic function? We have seen that the function f of x equals x squared, when defined from the real numbers to the real numbers, is neither one-to-one nor onto. However, we have also seen that it can become an onto function when its codomain is changed to the set of non-negative real numbers. But it is still not one-to-one because it continues to fail the horizontal line test, as we can see from the graph. But what if we restrict the domain to the positive real numbers and define the codomain to be the positive real numbers as well? In this case, the function becomes one-to-one because each positive output corresponds to exactly one positive input. At the same time, it is onto because every positive real number in the codomain has a positive real number as its input. Therefore, f of x equals x squared becomes a one-to-one correspondence when it is defined from the positive real numbers to the positive real numbers. This shows us an important point. The same mathematical rule can have different properties depending on how its domain and codomain are defined. The fundamental thing we need to remember here is we can classify almost any function by asking ourselves two simple questions. First, Are any outputs repeated? In other words, can two different inputs produce the same output? If the answer is yes, then the function is not injective, or in other words, it is not a one-to-one function. But if no output is repeated, then the function is one-to-one. Second, is every element of the codomain reached? In other words, does every element in the codomain have at least one input mapped to it? If the answer is no, then the function is not surjective, meaning it is not an onto function. But if every element of the codomain is reached, then the function is onto. Now, if we answer no to the first question, meaning no outputs are repeated, and yes to the second question, meaning every element of the codomain is reached, then the function is both one-to-one and onto. This is called a bijection, or a one-to-one correspondence, because every input is paired with exactly one unique output, and every output has exactly one corresponding input.
So why do mathematicians care so much about these labels? This all comes down to the concept of invertibility. Only bijective functions, or one-to-one correspondence functions, have inverses that are also functions. If a function isn't one-to-one, its reverse would have one input pointing to multiple outputs, which violates the very definition of a function. Remember, determining the type of a function often requires looking at the specified domain and codomain, not just the formula itself, meaning the interval where the function is defined has as much importance as the function itself for classification of function. Classification gives us the roadmap for how functions can be reversed or transformed. And we're done. Hopefully that makes some sense and helps you feel ready to identify these patterns in your homework. If this walkthrough was helpful, go ahead and hit that subscribe button to keep mastering math with us here at Rimetric Walkthrough. And I'll see you in the next video where we'll actually start calculating those inverse functions. Thanks for watching, and see you!